Hello, my name is Harry Crocker, and this is my lab 2 on lines of charge. The purpose of this lab was to develop a more accurate computational model to represent the experiment on transfer of charges between tapes from lab 1. In this presentation, I will go through the computational model, some mathematics behind it, and the results of the findings. The mathematical relationships used in this lab were Coulomb's law, which states that the net force is equal to k times the two charges divided by the radius squared times r hat, and then Newton's second law, which states that force is equal to mass times acceleration, where acceleration is equal to gravity, and Newton's third law, which states that for every force there's an equal and opposite reaction force, and superposition of charges, which states that a long line of charge can be divided into smaller divided segments, and the electric field can be found by summing those smaller segments. The assumptions that were made in this lab were to ignore air resistance, to treat a long tape as a point charge with all the charge concentrated at the center of the long tape X, assuming as well that each U-tape had about the same amount of charge evenly distributed along the length of the tape. The procedure was to lay a base tape strip on a flat surface, make two U-tapes by sticking an approximately 8-inch long tape to the base tape and ripping it off quickly, and then to test charge, place hand near tape, and then suspend one U-tape on top of two raised surfaces, and then finally hover the second U-tape below until the first U-tape raises up. The experimental data collected was the length of the tape at 0.2032 meters, the width of the tape at 0.02 meters, the mass of the tape at 2.032 times 10 to the negative fourth kilograms, and the distance between U-tapes, which was 0.0305 meters. And one of the observations made was that the momentum of the tape is not changing, so the net force is equal to 0. This slide shows some of the calculations that were made, the conversions for length, width, mass, and distance, and then also the force due to gravity was calculated there down on the left, and the charge as well there on the bottom right, resulting in 1.43 times 10 to the negative 8th coulombs. The results from these calculations were that the gravitational force was a 3D vector, 0, negative 1.993 times 10 to the negative third, comma 0, and then the magnitude of charge on the tape was 1.43 times 10 to the negative 8th coulombs. The computational model in Lab 2 treats these tapes as line charges. So first on the left, I inputted the mass as 2.032 e to the negative 4, but the charge is different. It's 2.83 e to the negative 8. So the next function to calculate is to calculate the electric field at the bottom, and I've created the tapes at a distance of 0.0305 meters apart in the y direction. On the right is the superposition of the charges. So the tape is divided into many DQs and n amount of segments. And then the electric field is calculated for each of them, and this is then summed up, and then to calculate the force, it's multiplied by the charge on the bottom of the tape. Then the errors are drawn. So in this method, instead of calculating it as a point charge, this computational model splits up the tape by using superposition of charges, and then uses Coulomb's law to calculate the charge for each segment, and then add it together to get the net electric field, which is then multiplied by the charge again to get the force. In this example, you can see that there are 100 segments, and the input charge was 1.43 e to the negative 8, and then the result was the magnitude of electric force was 5.09668 times e to the negative 8, and the gravitational force was 1.99339 e to the negative 3. Here, you can see the same number of segments, but the charge was increased to 2.83 e to the negative 8, and now both the magnitude of the electric force and magnitude of the gravitational force are roughly equal. What if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the one you got with your line charge model. So those are the two values there compared, and as you can see, the 2.83 is almost double what the first one is, and the estimates that were produced by these inputted values um, are different because the first one treats it as a point charge, whereas the second one treats it as a line of charge, all spread out evenly. And the 2.83 value is more accurate because it more closely represents what happens in real life.